Let us now, class 12, in this video talk about something called a p-n junction diode. Now, when do we say a p-n junction is a diode? So when the p-n junction, this p-n junction, of course with its depletion region, mind you, the moment you have a p-n junction, you will get a depletion region, remember that. So this p-n junction, of course, along with its depletion region, when it is connected to a power source like a battery, then it is called a p-n junction diode. Now, what is the meaning of a diode? A diode is actually a valve. The word in electronics for a valve, you can see, is diode. Now, what is a valve? A valve is something that allows the flow of anything, be it a gas, be it water. Okay, a valve is something that allows the flow of anything or something in just one direction. Likewise, you have a diode. A diode is an electronic device that allows flow of current, electrical current, of course, only in one direction. So diode is something that acts like a valve. You have a valve in the pressure cooker also. Okay, so if you have excess pressure inside the pressure cooker, if you have buildup of excess pressure inside the pressure cooker, the gas is allowed to come out of the pressure cooker through that valve. Okay, but of course the gas from outside is not allowed to enter the pressure cooker through the valve. Alright, so valve only allows in a pressure cooker the gas from the inside to flow in the outward direction. So likewise, a diode is something that allows flow of electrical current only in one direction, mind you. So this is like a valve for current. Okay. Alright, so p-n junction diode can be used in two ways. Alright. So one is called forward biasing. Biasing simply means in what sense or in what way is the battery connected to the p-n junction diode. Alright. So if the positive terminal of a battery is simply connected to the p-type of the semiconductor and the negative terminal thereby is connected to the n side of the semiconductor, then this type of connection of the battery to the p-n junction or the semiconductor is what is called forward biasing. Biasing simply means biasing simply means in what way is the battery connected. All right. So if to the p side of the semiconductor, positive terminal connected, and to the n side, negative terminal connected, then this is called forward biasing of the diode. All right. And we are going to see what happens in forward biasing. Of course, we are going to look into that. By the way, I forgot to tell you one thing in the last video. The symbol for a p-n junction diode, or simply for a p-n junction, is this. So this is your p-n junction along with its depletion region. This is the symbol for it. So it's like the horizontal triangle, and you have a vertical line through its tip. Okay, so this side will act like the p side of the semiconductor, and this is like your n side. So this is the symbolic representation of a p-n junction or a p-n junction diode. So you can see the forward biasing of the p-n junction diode also in here. So this is a p-n junction, this being its p side, this being its n side. So to the p side we have positive terminal connected, and to the n side we have negative terminal connected. So this is the symbolic representation for forward biasing of a p-n junction diode as well. All right. Now what happens when we forward bias a p-n junction diode? So to the p side we have positive terminal connected, to the n side we have negative terminal connected, and we know like charges, they repel. So these positive charges or holes are actually repelled, which are majority charge carriers on the p side, mind you. And these electrons, which are majority charge carriers on the n side, are repelled by the negative side. So what is happening is all the majority charge carriers from the n side are trying to move this way, and all the majority charge carriers from the p side are trying to move this way. So what is happening is there is of course the depletion region between the, on either side of the p-n junction, and the majority charge carriers from both the sides, from the p side also, from the n side also, they are trying to, move towards the p-n junction or move towards the depletion region. And thereby what happens is the depletion region is kind of squeezed in. It's kind of squeezed in. The depletion region is squeezed in. And thereby what happens is that the width of the depletion region decreases. You can understand it this way. So the depletion region is squeezed in because the majority charge carriers from either side are coming towards it. All right, the depletion region gets decreased in size, gets squeezed in, and thereby the potential barrier is also going on decreasing. The size of the potential barrier or the depletion region, mind you, goes on decreasing, and what happens is eventually the majority charge carriers from the n side, or you can also look at in terms of the holes, they simply, because this is the power source, so this is like providing the energy for the holes and the electrons to eventually overcome the potential barrier. So what happens is, these electrons and these holes, after gaining electrons or after being repelled by this power source, by the respective terminals of the power source, what happens is they jump over the potential barrier, and what happens is all of these electrons from the n side, they reach the p side. Okay, majority charge carriers from the n side, they reach the p side, and likewise the majority charge carriers from the p side, they reach the n side. So you have holes now in here, no longer electrons, you have holes in here, and you have electrons on the p side. All right, now once the majority charge carriers from either side reaches the respective other sides, okay, so holes reaches, majority charge carriers holes from the p side, they reach the n side. Majority charge carriers from the n side, which are electrons, they reach the p side. And the electrons now, on reaching the p side, they are readily attracted by the positive terminal of the battery. Or you can also understand it this way: the majority charge carriers on the p side, which are holes, on reaching the n side, they are readily attracted by the negative terminal. So what is happening is, there is flow of majority charge carriers, so to say, through the potential barrier or through the p-n junction. So electrons are moving this way. All right, means what is happening is there is flow of current through the p-n junction diode in this direction, in a direction opposite to the direction of movement of electrons. Electrons are moving towards our left hand side, so to say current is flowing through the p-n junction towards our right hand side. So basically there is flow of current through the p-n junction diode when we forward bias the p-n junction diode itself. Okay, and this flow of current, mind you, is because of the flow of majority charge carriers. All right, so in forward biasing there is flow of current because of flow of majority charge carriers. All right, now there is something called forward bias characteristics. Okay, so this is exactly what we discussed just now. So we what happens is, this is the scenario, like this is a variable resistor I have shown in the picture. Okay, you may exclude this and simply connect it, the p type of the semiconductor, to the battery, like in this example what I am talking about is. All right, so we see that when we forward bias the p-n junction, there is flow of current due to majority charge carriers, and this current is in the order of milliamperes. Okay, exactly the same picture here in symbolic representation of p-n junction diode. So what is this forward bias characteristics? Forward bias characteristics is a graph. It is the plot of current versus voltage. So as we go on, this is a variable resistor. When we go on changing the value of the resistance, variable resistor, all right, what happens is the potential difference. When we go on changing this potential difference, you can also understand it this way. When we go on changing the potential difference, what is happening is the holes, more and more holes gets pushed this way, more and more electrons gets pushed this way. Okay, so we can plot the current flowing through the p-n junction due to majority charge carriers versus voltage. So as we go on increasing the voltage, what we see is initially there is very small current. Okay, and all of a sudden what happens is there is a large flow of current. Okay, so this current is in the order of milliamperes, remember. So this plot of I versus V in case of forward biasing of p-n junction diode is what is called forward bias characteristics. Okay, so this is an important graph for you all. You might get asked to draw this forward bias characteristics only as well. So you need to know this graph. Now, there is something called reverse biasing. If we have forward biasing, there is something called reverse biasing as well. If we have majority, we have minority. Majority charge carriers, minority charge carriers. So if we have forward biasing, we have reverse biasing as well. So we have this p-n junction along with its depletion region, which is connected to a power source now. Now in reverse bias, what happens is, okay, let us again look at what forward bias is. In forward biasing, the p type is connected to the positive terminal, n type connected to the negative terminal. In reverse biasing, of course, since it's the reverse of forward, so therefore is the opposite of forward. So the P type is now connected to the negative terminal, as you can see, and the N type is connected to the positive terminal. Now what happens when this is true? When the negative terminal is connected to the P type, positive terminal connected to the N type, so what happens is majority charge carriers that are on the N side, which are electrons, they are attracted by the positive terminal. Likewise, majority charge carriers on the P side, which are holes, they are attracted by the negative terminal. So there is no flow of, as you can see, there is no flow of majority charge carriers through the PN junction. Okay, all of the electrons that are here, majority charge carriers, they are attracted by the positive terminal. All of the holes, majority charge carriers on the P side, are attracted by the negative terminal. So these majority charge carriers are not flowing through the PN junction. But what is true, what other thing that happens is, on the P side, we have some amount of electrons, which are minority charge carriers. Okay, we have already seen on the P side, we have minority charge carriers. On N-type semiconductor, we have minority charge carriers to be holes. On P-type semiconductor, we have minority charge carriers to be electrons. So, on the P side, we have electrons as minority charge carriers. Very small amount of minority charge carriers compared to the majority charge carriers, mind you. Likewise, on the N side, we have holes as minority charge carriers. So, these minority charge carriers, electrons on the P side, they are now repelled by the negative terminal. And these positive holes on the N side, which are minority charge carriers, are repelled by the positive terminal. So these electrons, they flow towards the depletion region and towards the PN junction. They possess energy because of this power source, and they possess energy to overcome the depletion region. All right, and these holes in turn, which are minority charge carriers on the N side, they move towards the depletion region and the PN junction, and they overcome the potential barrier because of energy gained through this power source. So the minority charge carriers are now overcoming the potential barrier or crossing the depletion region and the PN junction. Okay, so what is happening in reverse bias is there is again flow of current, which can be measured in this ammeter here. Okay, so there is again flow of current through the PN junction under reverse bias condition as well, but this flow of current is due to the minority charge carriers, remember. So when the charge carriers, they flow through the PN junction, only then, a current flows through the diode, remember. So here current is flowing because of flow of minority charge carriers. So we can see the symbolic representation of reverse bias. The P side being connected to the negative terminal, the N side being connected to the positive terminal. Okay, so likewise, in case of forward bias, we have forward bias characteristics. We have reverse bias characteristics in here. Now what happens in reverse bias characteristics? Again, this is a plot of current versus voltage. So I have the combined forward and reverse bias characteristics over here. This is first quadrant picture. Okay, is that for forward biasing? Current versus voltage. Current is in the order of milliamperes. We've already seen that here. Current is in the order of milliamperes. So the same picture, I've combined both reverse bias and forward bias characteristics here. So this is for the forward bias thing. Now this third quadrant picture is for the reverse bias characteristics. Now what we see is again a plot of current versus voltage, but the current, since this current under reverse bias condition is due to the flow of minority charge carriers, this is a very small amount of current flowing, which is in the order of microamperes. Now microamperes is 1000 times lesser than milliamperes, remember. So the current that flows under reverse bias condition is in the order of microamperes, which is 1000 times lesser than the current that was flowing in forward bias condition, remember. So it's like current is flowing through the diode only in forward bias condition, which is in the order of milliamperes. In reverse bias condition, since only a negligible amount of current flows, which is in the order of microamperes, 1000 times lesser than milliamperes, so we say it's like through the diode, current is only flowing in one direction. That is true under forward bias condition only. Therefore, it is called a diode, remember. Although under reverse bias, we see that very small amount of current is flowing in the order of microamperes. It's like this is negligible amount of current. So therefore, we consider it, as if there is no flow of current itself. All right, so it's as if there is only current flowing through the diode in one direction. That is under forward bias condition. Okay, so what happens in reverse bias? As we go on increasing the voltage, this voltage, okay, so we've considered this to be positive voltage when the positive terminal is connected to P-type, negative terminal connected to N-type. Say this is positive voltage, the increase in voltage, is positive voltage. Then the increase in voltage under this condition, when negative terminal connected to P-type, positive terminal connected to N-type, the increase in voltage under this condition is increase in negative direction of voltage. So when we increase the voltage under this condition, what happens is there is negligible amount of current, very negligible. In my picture, this is also more actually. This is almost as parallel to the x-axis, remember, negative x-axis. So it's something like this, almost as parallel to negative x-axis. Okay. So very almost zero amount of current as you go on increasing the voltage here. All right. Minority charge carrier is current flowing, but current flowing due to minority charge carriers, but negligible amount of current flowing, almost equal to zero. There is no increase in current, as you can see, as the voltage increases. Now, after a certain increase in value of voltage, what happens is there is a huge amount of current flowing. All right. This huge amount of current flowing, this thing, you can see all of a sudden there is no current flowing. All of a sudden there is huge amount of current flowing. This is actually called avalanche breakdown. This is called avalanche breakdown. B-R-E-A-K-D-O-W-N. Avalanche breakdown. Now you all know what an avalanche is. It's like a huge landslide of snow. All right. So all of a sudden huge amount of current starts flowing. Now there is a reason for this. What happens is we know in an extrinsic semiconductor, be it P-type semiconductor, N-type semiconductor, okay, the electrons are bound by covalent bonds. I'm trying to tell you why is there an avalanche breakdown. So as we go on increasing the value of voltage here, negative voltage in the reverse bias, what happens is this provides enough energy for the covalent bonds are weak bonds compared to electrovalent bonds. You must have studied this in chemistry. So this negative voltage provides enough energy to break the covalent bonds. So that enough energy provided due to the increase in voltage under reverse bias condition provides enough energy to break the covalent bonds. And when the covalent bonds are broken, be it P-type or N-type, lots of electrons are released and these electrons become free electrons. And it is these free electrons that have come, okay, due to the breaking up of the covalent bonds that helps in the passage of huge amount of current. All right. And thereby you have the avalanche breakdown. All right. So you have huge number of electrons generated here, huge number of electrons generated here. Okay. So those electrons from the P side, they are repelled by the negative terminal. All right. So huge amount of electrons that have formed on P side due to covalent bonds breaking up. So those electrons pass towards, repelled by the negative terminal, they move towards the N side and they are readily attracted by the positive terminal. And thereby you have electrons, huge number of electrons flowing through the potential barrier or PN junction, and thereby you have the avalanche breakdown. The concept of avalanche breakdown is not there in your syllabus, okay, but still I'm giving you a brief idea about it. This is how huge amount of current starts flowing in the reverse bias condition. So this is about forward biasing and reverse biasing of a PN junction diode. And this is how a PN junction acts like a diode, allowing current only to flow in one direction, that is under the forward bias condition. Negligible current flows in the reverse bias condition, and thereby it is called a diode minding. Okay, so we are only talking about up to here. Only up to here is there in the syllabus. Avalanche breakdown, although I've spoken about it, is actually not there in the syllabus.